Complex compounds are a special class of compounds in which the metal atoms or ions are bound to a number of anions or neutral molecules. In modern terminology, these compounds are called coordination compounds. Coordination compounds or complex compounds are a type of addition compounds. When two or more stable compounds are allowed to combine in stoichiometric ratios, crystalline compounds are formed. These are known as addition or molecular compounds. For example, when saturated solutions of potassium sulfate and aluminium sulfate are mixed and heated till the crystallization point is reached, we get the well-known compound potash alum. Similarly, if we add a solution of potassium cyanide to a white precipitate of nickel cyanide, the precipitate immediately dissolves, and a red-orange solution of a new compound is obtained. On the basis of their nature, addition or molecular compounds are divided into two categories. They are double salts and coordination or complex compounds. Double salts are molecular compounds that are stable in the solid state but break down into individual constituents when dissolved in water. Note that the individual properties of the constituents are not lost in these compounds. For example, an aqueous solution of potash alum will give the tests for K+, Al+3 and SO4-2 ions. Other common examples of this class include carnallite and Moore's salt. On the other hand, coordination compounds are molecular compounds that retain their identity even when dissolved in water. Note that the individual properties of the constituents are lost in these compounds. For example, when potassium ferrocyanide is dissolved in water, it does not give the usual tests for Fe+2 and Cn- ions, indicating that the ion FeCN6-4 does not dissociate into Fe+2 and Cn- ions. Other familiar examples for nickel, copper, and silver are shown here. Actually, these ions are present in the form of a new ion called a complex ion. Compounds that have complex ions are called complex compounds. as the central metal ion in the complex ion forms dative or coordinate covalent bonds with the species surrounding it. Complex ions are also known as coordinate ions, and hence the corresponding compounds as coordinate compounds. Transition metals show a greater tendency to form complex compounds. This is due to the relatively smaller size of the metal ions, high ionic charges, and the availability of vacant d orbitals for bond formation. Coordination compounds form the backbone of modern inorganic and bioinorganic chemistry and chemical industry. Naturally occurring complex compounds are vital to living organisms. For example, chlorophyll is a coordination complex of magnesium. Hemoglobin is a coordination complex of iron, while vitamin B12 is a coordination complex of cobalt. Complex compounds find extensive use in electroplating, metallurgical processes, textile dyeing, and medicinal chemistry. Apart from that, they also find applications as industrial catalysts and analytical reagents. A coordination complex is the product of a Lewis acid-base reaction, in which a central metal atom or ion forms coordinate covalent bonds with neutral molecules or anions called ligands. Similar to the terms central metal and ligand, there are some other terms like coordination number, coordination sphere, coordination polyhedron, oxidation number, homoleptic complex, and heteroleptic complex, which are used with reference to coordinate compounds. Hence, you must get familiarized with these terms to understand different aspects of coordination chemistry. So let's go through these terms in detail. The first term is central metal atom or ion. The atom or ion to which one or more neutral molecules or anions are attached in a definite geometrical arrangement around it is called the central atom or ion. For example, the central metal ion in NiNH3 6+2 is Ni plus 2, in FeCN6 is Fe plus 3, and in COCl6 it is the CO plus 3 ion. As the central metal atom or ion acts as an electron pair acceptor, it is also referred to as a Lewis acid. Another important term is ligand. A ligand is any atom, ion, or molecule capable of donating a pair of electrons to the central atom. A ligand is also known as a coordination group. As ligands are electron pair donors, they act as Lewis bases. Ligands may be simple ions such as halide ions, small molecules such as water or ammonia, or large molecules such as ethane 1,2-diamine or ethylene diamine tetraacetate ion. The number of atoms in a ligand that bind to the central atom in a complex is referred to as denticity. When a ligand is bound to a metal ion through a single donor atom, as with a chloride ion, a water molecule or an ammonia molecule, the ligand is said to be unidentate. Ligands that contain two donor atoms are known as bidentate or didentate. Common examples of didentate ligands are ethane 1,2-diamine, dimethyl glyoxime, and oxalate ion. As you can see, these ligands have two donor atoms that can simultaneously bind to the central metal atom. Ligands with several donor atoms are called polydentate or multidentate ligands. A classic example of polydentate ligand is the hexadentate ligand, ethylene diamine tetraacetate ion, EDTA. You can see from its structure that it binds to the central metal ion through 2 nitrogen and 4 oxygen atoms. Ligands like ethylene diamine and EDTA, which have lone pairs of electrons on more than one atom, are capable of binding to the central metal atom or ion through more than one coordinate covalent bond. Such ligands are called chelating ligands. Some ligands have two different types of potential donor atoms, but use only one of them to form a coordinate covalent bond with the metal ion. Such ligands are called ambidentate ligands. The NO2- ion is one such ambidentate ligand capable of coordinating to the metal atom or ion through the nitrogen or oxygen atom. Similarly, the SCN- ion can coordinate through the sulfur or nitrogen atom. Now, let's look at another important term, coordination number. The total number of ligand donor atoms to which the metal is directly bonded is known as the coordination number of that ion. For example, the coordination number of silver in the complex ion AgNH32+ is 2, while that of nickel in the NiNH3 4+2 ion is 4. Similarly, the coordination number of copper in CuEn2+2, a complex with a didentate ligand, is 4, while that of cobalt in COC2O4 3-3, another complex with a didentate ligand, is 6. Coordination entity or coordination sphere is a common term we use with reference to complexes. The central metal atom and the ligands attached to it are collectively termed as the coordination sphere or coordination entity. For example, in the complex K4FeCN6, Fe, along with the 6 cyanide ligands, is the coordination sphere. the coordination sphere is written inside square brackets, while the ionizable groups are written outside the bracket and are called counterions. For example, in the complex K2NiCl4, the coordination sphere is NiCl4 minus 2, and the counterion is potassium. Coordination polyhedron is another term we use in coordination chemistry. In a coordination sphere or entity, the ligands are attached to the central metal ion in such a way that it gives a definite geometry to the complex. Thus, in a coordination entity, the solid figure defined by the position of the ligand atoms directly attached to the central atom or ion is known as the coordination polyhedron. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. For example, CONH3 6 plus 3 is octahedral. NiCO4 is tetrahedral, while PtCl4 minus 2 is square planar. One of the most important terms we often use is oxidation number of the central atom. The oxidation number of the central metal atom in a complex is defined as the electric charge it would carry if all the ligands were removed along with the electron pairs that are shared with the central atom. The oxidation number is represented by a Roman numeral in parentheses after the name of the central metal atom. For example, the oxidation number of iron in FeCN6-3 is plus 3, and it is written as Fe3. Let us learn the method to determine the oxidation number of the central metal atom in a complex. Let's take K4FeCN6 as an example. As the complex has 4 monovalent cations outside the coordination sphere, the complex ion carries a charge of minus 4, that is, FeCN6 minus 4. Let's assume the oxidation number of the central metal atom as X. The cyanide ion is a monodentate negative ion. Knowing that the complex carries a charge of minus 4 and has 6 monodentate negative ions, the oxidation number of iron can be determined as X plus 6 multiplied by minus 1, which is equal to minus 4. On simplification, we get X is equal to plus 2. Thus, the oxidation state of iron in the given complex is plus 2. Here is a simple problem for you. Calculate the oxidation number of the metal atoms in the complexes given here. In the first case, there are 3 cations outside the coordination sphere. Hence, the charge on the complex ion is minus 3. The oxalate ion is a bidentate ligand. Each oxalate ion carries a charge of minus 2. The oxidation number of iron, which is assumed as X, is calculated as X plus 3 multiplied by minus 2, which is equal to minus 3. On simplification, we get X is equal to plus 3. Hence, the oxidation number of iron is plus 3. Similarly, the oxidation number of copper and silver in the other two complexes are calculated as +2 and +1 as shown. Finally, let's look at the terms homoleptic complex and heteroleptic complex. A complex in which a metal is bound to only one type of ligand atoms is known as a homoleptic complex. For example, CONH3 6 plus 3 and FeCN 6 minus 3. On the other hand, a complex in which a metal is bound to more than one kind of ligand atoms is called a heteroleptic complex. For example, CONH3 4ClBr plus 1 and CrNH3 4Cl2 plus 1. Coordination compounds. The names and formulae of coordination compounds are written by employing the rules published by the International Union of Pure and Applied Chemistry, or IUPAC in short. Let's look at the rules framed by IUPAC for writing the formula of a complex. The first rule is the formula of the cation, whether it is simple or complex, is written first, followed by that of the anion. For example, in the complex shown here, the cation sodium is written first, followed by the anionic coordination entity. Similarly, in the complex containing a complex cation and a complex anion shown here, the complex cation AgNH32 is written first, followed by the complex anion AgCN2. The second rule is that within the coordination sphere, the symbol of the central atom is written first, followed by the symbols or formulas for the ligands in alphabetical order, irrespective of the charge on them. For example, in the complex shown here, the metal atom cobalt is written first, followed by the ligands ammonia and chloride. Polydentate ligands are also listed alphabetically. While listing in alphabetical order, the first letter of the abbreviation of the ligands is used to determine their position. For example, if a complex contains chloride and ethane 1,2-diamine, which is abbreviated as EN, then in alphabetical order, chloride is written first, followed by ethane 1,2-diamine. Another rule is that the formula for the entire coordination sphere is enclosed in square brackets. For example, in the complex shown here, the coordination sphere containing the metal atom copper with 4 bromine atoms are enclosed in square brackets. The cation potassium is written outside the coordination sphere. The formulae for polyatomic ligands and the abbreviations used for the ligands are enclosed in brackets. For example, EN, EDTA, PY, etc. are enclosed in brackets. For example, in the complex of cobalt shown here, the coordination entity contains the polyatomic ammonia ligand and the abbreviated ethane 1,2-diamine ligand enclosed in brackets. One more rule is within a coordination sphere, the metal atom as well as the ligands are listed without any space between them. For example, in the complex of cobalt shown here, the ligands ammonia, water and chloride are listed without any space between them. Yet another rule is that when the formula for a cationic or anionic coordination sphere is to be written without that of the counterion, then the charge with the number before the sign is written as a right superscript outside square brackets. For example, the complex ions of cobalt and chromium with the charge on the respective ions are shown here. Now let's see the IUPAC recommendations for writing the names of complexes. The first rule is, for coordination compounds that are ionic, that is, the coordination sphere serves either as the cation or the anion of the ionic substance, the cation is named first and separated by a space from the anion. For example, in the complex K4FeCN6, where the coordination sphere is an anion, the cation, potassium, is named first and separated by a space from the name of the anion. On the other hand, in a complex such as CONH3,6Cl3, where the coordination sphere is a cation, the cationic coordination sphere is named first, followed by the name of the counter anion, chloride. The second rule is, while naming the coordination sphere, ligands are named first, followed by the name of the central metal atom or ion with its oxidation state in Roman numerals in parentheses. Remember that irrespective of the charge on the ligands, they are named in alphabetical order. For example, in the complex PT-NH3-2Cl4, the ammonia ligands are named before the chloride ligands according to the alphabetical order, followed by the name of the metal ion with its oxidation number enclosed in brackets. IUPAC has also proposed certain rules for naming ligands. Anionic ligands are given names that end in the letter O. When the name of the free uncoordinated anion ends in ate, the name of the ligand is changed to end in ato, ATO. For example, the anion acetate is named acetato, sulfate as sulfato, thiocyanate as thiocyanato, and carbonate as carbonato. When the name of the free uncoordinated anion ends in ide, IDE, the ligand name is changed to end in ido, IDO. For example, the anion fluoride is named fluorido, chloride as chlorido, bromide as bromido, and iodide as iodido. Similarly, nitride is named nitrido, amide as amido, and azide as azido. Neutral ligands are given the same name as the uncoordinated molecule. For example, pyridine, dinitrogen, dioxygen, and triphenylphosphine. However, some neutral ligands are given special names. They are aqua for water, amine for ammonia, nitrosyl for nitric oxide, and carbonyl for carbon monoxide. Positive ligands, such as nitronium, hydrazinium, and nitrosodium, are named as such without any change. Another rule says, if several ligands of the same type are attached to the central metal atom, then their number is indicated by the prefixes di, tri, tetra, penta, etc. For example, in the complex CONH3, 3H2O Cl2. The 3-amine and 2-chlorido ligands are indicated by the prefixes tri and di, respectively. However, if the name of the ligand in question already includes a numerical prefix, then the prefixes like bis, tris, tetrachis, and pentachis are used. For example, the complex RuCl3-PPH33 is named as tris-triphenylphosphine trichlorido-ruthenium 3. Here's another rule. When the coordination entity is either neutral or cationic, the usual name of the metal is used. For example, the neutral complex shown here is named triamine trichlorido cobalt 3. Similarly, the cationic complex CrH2O4Cl2Cl is named tetra-aqua dichloridochromium 3 chloride. Note that, in either case, the usual name of the metal is retained. However, when the coordination entity is an anion, the name of the metal ends with the suffix -ate. For example, the anionic complex NaPtNH3 is named as sodium triamine trichlorido platinate 2. For some metals such as iron, copper, silver, and gold, their Latin names ferrate, cuprate, argentate, and aurate are used. For example, the complex K2CuCl4 is named potassium tetrachlorido cuprate 2. Similarly, the complex NaAgCN2 is named sodium dicyanoargentate 1. Now is the time for practice. Apply IUPAC rules for writing the formulae in the first question and for writing the IUPAC names for the given complexes in the second question. Question 1. Write the formulae for these coordination compounds. Tetraamine aqua chloridocobalt 3 chloride. Dichlorido bis ethane 1,2-diamine cobalt 3. Tetracarbonyl nickel 0. Question 2. Write the IUPAC names of these coordination compounds. Let's write the formula for the first compound.